Okay. So we were talking about amines and enamines. We have our functional groups. So we talked about in the past carbonyl, CO double bond, and enol, alkane and alcohol. And now we are asking the question, what if we just make it nitrogen? So if we have a carbon nitrogen double bond, it's called an imine, and we use it with an I sound to distinguish it from an enamine, where we're doing like the big E sound, enamine. Enamine is like an alkene and an amine together. And another kind of refresher of functional groups you've seen before, primary and secondary amines. So a primary amine, an example would be this one right here, ethylamine, where it's a nitrogen attached to one carbon thing. So a nitrogen attached to one carbon thing is a primary amine. A nitrogen attached to two carbon things is a secondary. And then you could also have a nitrogen attached to three carbon things, tertiary amine. We have some side characters that are going to join us in these mechanisms. So if we have an imine and we protonate it, it's an iminium. And then we have a hemiaminal, which is when we have an amine and an alcohol on the same carbon. The first time I heard the word hemiaminal, I think I raised my hand and I said, gesundheit. What did you just say? What was this involuntary utterance that left your mouth? Hemiaminal? That seems ridiculous. This made me want to quit chemistry. But now I think it's kind of fun. And she's kind of a main player in the mechanism, so we need to know what she looks like. The other piece of nomenclature, this was not in lecture. It's going to be in lecture 10. We're not going to test you on it, but it's something that I think is going to be helpful for understanding these mechanisms. So if we have an imine or if we have a carbonyl, either one, if we go one carbon away from the double bond, this is called the alpha position. So this is an alpha carbon, and these are alpha hydrogens. So one away from the double bond is the alpha position. If we went two away, it would be the beta position, a beta carbon, beta hydrogens. You'll see why that's going to be coming back and why it's going to be helpful in a bit. But any questions on who's playing the game? Who the functional groups are? This time nomenclature stuff. I just want to make sure that this is being captured every Zoom. It is. Good. Okay, let's keep plowing. So we want to know how to make these amines and enamine new functional groups because they're cool and we want the cool new things. So if we start off with a ketone or aldehyde and we add a primary amine, we get an imine. If we add a secondary amine, we get an enamine. So that's kind of the big idea that you need to know of if we're reacting with a primary amine, that's what controls for the imine, and then a secondary amine is the enamine. As you can see, that just sentence right there, all these things sound alike, and they all have nitrogen. So making sure that they are very clear, I think will be helpful. The mechanism for these are exactly the same, except for the last step. So let's talk through what happens. So our amine is going to attack our carbonyl, push up, and we make a tetrahedral intermediate. When we are at the tetrahedral intermediate, we're going to have a minus and plus, and we are going to do a proton transfer to make them both neutral. So this is the abbreviation you can use from now and forevermore of if you start with something and want to do a proton transfer, you just have to draw the structure, arrows with PT, and draw the next structure. You do not need to draw like something deprotonating this and then something protonating here. You can just skip that now because you've proven by taking the first exam that you all know how to do those arrows. Then specifically, this neutral thing that we formed is the hemiaminal, the side character. She is an important waypoint in this mechanism because she is a neutral compound. She's one of the more stable intermediates here. And if you do not draw the neutral one, we will take off points. So that's why I said we should give her a name because she's important and because she costs points if we don't include her. Hemiaminal. So once we're at the neutral hemiaminal, what we need to do now is we need to get this oxygen out of here. We protonate it, make it a better leaving group. And then we do a lone pair push and form our iminium here. So most of these steps should look familiar. And then if you had a primary amine, then this nitrogen that has 4 bonds, one of them is to a hydrogen. So the thing that we could do really easily is we just deprotonate at the nitrogen, and then we are at our imine product. So that is the final step for the imine formation. However, if we had a secondary amine attack, this nitrogen is attached to 2 R groups. And so all we have are carbon nitrogen bonds, and those are much harder to break than a CH bond or an NH bond. And so what we're going to do is we're going to go to the neighbor one over, which is the alpha position, and we are going to deprotonate at the alpha position. When we deprotonate, when we take this H, these electrons are going to go and form a carbon-carbon double bond, which frees these electrons up to go up to the nitrogen. And just like that, we make an enamine. So the reason I think that knowing that alpha name is because now instead of saying, well, you go over to the next one and then you take the H, like you do an alpha deprotonation. Like it just gives you language to talk about it. Questions about this mechanism? Yeah. For this, yeah. Yeah, see, I did the one as if it was secondary, and I said, or it could be this. Okay. It's only when you're going to be at the tetrahedral intermediate, and it's only when you're taking it off one, putting it on another. One also thing that I would like to flag is you can't go directly from here to here, because that's not doing 2 protons, it's doing 3. You're putting 2 on here and then taking 1 off here. That's not a proton transfer. It has to be 1 on, 1 off. Yeah. Any other questions about the synthesis mechanism? We'll see when we do it together. Then we need to have the reverse reaction because it's reversible. So the thing that you add to an amine or enamine to break it up and get our ketone aldehyde and our amine back is you add H3O plus. And the reason why you specifically need to write H3O plus and not just like acid is because you need a source of oxygen to form the carbonyl. Because starting off with an amine or enamine, there's no oxygen. I'm not going to go in detail on the mechanism, but it is truly the exact reverse. So like the synthesis, you had a different last step, but everything else was the same. Here you have a different first step where you're just undoing what you did previously. So an amine, you protonate it, and then an enamine, you push down and protonate at the alpha position. You do an alpha protonation instead of an alpha deprotonation. So this has 2 hydrogens instead of just 1. And then the rest of it is the exact same reverse of what we did. So to do this, these amine and enamine are often tested as like mechanism questions. And the mechanism is also going to show up again in lecture 10. So I thought that we could do the hardest mechanism that was amine, enamine on the P set. Just so that you get experience doing the hard one together, we can work on it together. So this is going to be page 8. And let's talk through some of it together and do some analysis and try to figure it out. So what functional group do we have in our starting material? Aldehydes, great. What functional groups do we have in our product? I know you're tempted because there are 3 of them that sound really similar. They all have nitrogen. So amide is going to have a carbonyl. Yeah. Just an amine. So amine would be something like this, right? But she's also next to an alkene, right? So if we have an alkene and an amine, we have an enamine. Yes. And if we had an imine, it would look like a CN double bond, but we don't have a double bond to the nitrogen, so we do not have an imine. The interesting thing here is we have an enamine this way, and we also have an enamine that way. And that's why this is going to be harder than what we just saw, like the basic mechanism. What other functional group do we have over this arrow? Yep. Yep. And is it a primary, secondary, or tertiary? What? Primary. Good. So we said that a primary amine and an aldehyde make what functional group? Amine, right? But we have enamines in the product. So, something's up with her. But what I'd like you to do is take a minute, and I don't want you to do the full mechanism, but what I want you to do is I want you to just try to predict what the product of this carbonyl and this amine would be as an amine. And to do that, I'm going to do like the general case with you. So the general case is if I had this and this, and I was trying to predict the product, what I would do is I would erase the carbonyl, make a double bond to a nitrogen, and add whatever my R group was. And do you see how if I follow those fake mechanism steps, I can just write what the product is? Again, erasing the double bond, put a double bond to a nitrogen, add the R group. So try doing that with this reaction. And I want you to write what the amine would be formed. And let's just say either one could happen. Let's say we're reacting this left aldehyde with this amine. What is the amine that is formed from that? So I erase the carbonyl and I put a double into nitrogen. And what's the R group that I should add here? A methyl, good. No words left her mouth, but she said. Okay, so interesting. This is not an enamine. So let's try to map what we have so far onto the products. Well, I'm willing to put money that this nitrogen is this nitrogen. Okay, well then, do we have the same number of carbons in this intermediate in the product? Yeah, we do. So we have these four, and I might label the one attached to the nitrogen green. And is there a way to tell whether the green one's this left one or the right one? Does it matter? No, they're functionally equivalent. So we have this, and then we connect around. And ooh, I see something interesting in terms of these connectivities. So over here, this yellow never connects to the blue. But here, the yellow connects to the blue. So what I know is we need to make a sigma CN bond. Sigma CN bond. And also, we go from an open chain to a ring. So how do we form rings? What type of reactions form rings? Anyone? I did some cyclic acetal hemiacetal things. What made it a cyclic hemiacetal or acetal rather than just a hemiacetal or acetal? Intramolecular. So this molecule needs to attack itself. And this is where the first weird step is. The first weird step is instead of having an amine attack the carbonyl, we can actually have this imine because it has a lone pair circle around and attack. That is the new step that's like, whoa, that would have been hard to think of on our own. But do we see how we were able to kind of get to the fact that we needed to do something there? Because we know that these have to connect somehow, right? So we know this nitrogen needs to connect with this carbon. So now the hard part is, okay, how do we draw the next thing? Because making a ring is difficult, like drawing it physically. So what I do is I number all of the things that are going to be connected. And I see I'm going to be connecting 5 things into a ring. So we're going to have a pentagon. And then I am just going to draw my little pentagon. And I'm going to make one of the things in the pentagon nitrogen. Then I keep my numbers. I'm going to do 1, 2, 3, 4, 5. And then I ask myself, what else do I need to put on this ring? Well, I know that between 1 and 2, there's a double bond because I didn't break that. Um, I know that there's a methyl on the nitrogen, which I'm just going to write as a line. I'm not going to write out the CH3. Carbon 5 is going to have something on it. What's carbon 5 going to have on it? It's going to have an O that was still here. And it's only going to be a single bond now because we broke the double bond. So we're going to have an O minus. And then are we done, or is there anything else we need to add to this molecule? Yep, it does, because now it has 4 bonds. Okay, interesting. Very interesting. So at this point, let's see kind of how far we are away. Well, one thing I'm noticing is here we have a double bond with nitrogen again, and we do not have that in the product over here. So we need to get rid of her. So where's a situation where we saw something like this? Or actually, before we do that, we also have a negative charge and we're in slightly acidic conditions. So what do you think we're going to do next? Basically, that's my question. Protonate, is that what I heard? So we're just going to go and grab a proton from something in the solution. So you can do H-sol, you can do HA for a general acid, something. And we've neutralized it. And then we're still back to the difficult question of what do we do? But now we have 1 fewer charge, which is nice. So where have we seen a nitrogen with 4 carbon bonds and a positive charge that we tried to get rid of? Was this in the amine mechanism or the enamine one? I see you mouthing words again. No? What about you? The enamine. Remember, our last step there was that weird one where we said, hey, we don't have a proton that we can easily just get off. So we're going to do that special alpha deprotonation. And that's going to let us make our neutral nitrogen. So if we go back over to the problem, the alpha position is going to be 1 away from the double bond. So we go 1 over alpha position. I'm going to write the hydrogen out here. And something in the solution, or a general base, is going to go and deprotonate that. When we do that, the electrons are going to form a carbon-carbon bond, and then we can push electrons up to nitrogen so that she is more happy. And now we would say, whoa, we're more than halfway there. I don't think we're even living on a prayer. We're doing pretty well. We're getting there. So now what's the other big thing that you see needs to leave? What is in this intermediate that's not in the product? The OH, right? So we need to make it leave. What is the way that we've made things leave in the past? If only we had a tetrafeature intermediate where we had something that could do the lone pair pushing, and then we could kick off a leaving group. Oh my gosh! Who is she? She's the side character. What's her name? She's a hemiamine now. Yes. Yes. And she was kind of hidden. It's like, oh my gosh, we stumbled into being halfway through an amine-enamine mechanism. We have the hemiamine now. Wow. She just exists. Yeah. Because we have an amine on one side and an OH on the other. Yeah. It's weird to spot. And that's why I like to be like, oh my God, big reveal. Now question, are we just going to kick off OH if we're in slightly acidic conditions? Because normally we do this pH around 5. Why would we not want to kick off something with a negative charge in acid? Sure, work. I think in the way I would think about it is it's just faster to kick it off when it's protonated and we're in acid. So let's protonate it and then do our lone pair push. Okay, so our nitrogen has gotten fed up and wants this water out of here. The lone pair pushes in, kicks off the water. And then what we have, we are so close. So we have this and our product. I'm going to kind of rotate this. I'm just going to rewrite it. Our product looks very, very close to this, but it's kind of just like we have our double bond in the wrong place. And yet again, we have a nitrogen, 4 bonds to carbons, and we want to make it neutral. So what do we do? Hmm? Oh, you were just working through it. You weren't raising your hand. Proton transfer. Well, how would a proton transfer, like what is the thing that would take a hydrogen and here there's no hydrogen to take off here? What's the thing that we did earlier when we had the same thing? What do we call that? An alpha deprotonation. Oh, okay, work. Then yes, alpha deprotonation. And again, this is the thing where I think having the name of it, like it lets you know that that's a tool in your arsenal. So we draw out the alpha H. Something in the solution comes along, deprotonates it, and we are in it. So we've done most of this mechanism. I skipped the first steps because this any information is straight up the exact arrows from lecture slides from the little section bit. And so like the beginning portion where you make the first imine, that I think you can do on ground. I wanted to do these kind of hard, tricky ones with you and just point out some of the trends that have popped up of these alpha deprotonations forming the hemiaminal elm and some of the strategy of like piecing together how we get to some of those weird steps. Like this one is, I think, our weirdest step. Questions on this mech? I shouldn't say mechanism. Yeah, you do it from the side next to the carbon because you're making a carbon-carbon bond. So I think if we had something else here, like we had carbons here and we had a hydrogen here, then hi. Hello? What? Oh, she just auto turned off. Oh no. So what I think has happened is I think the projector has overheated. So take a minute, stretch your legs, and I'm going to try rolling over the TV and trying it on the TV. But to answer your question, there was only one carbon neighbor to oh, whose question was it? Yours? There's only one carbon over that isn't. I don't think we've stumbled upon a solution if it's actually overheating, because I think that she'll just shut off again in a minute. But knock on wood. You're talking about this position, or were you talking about this? Okay. So here, the alpha position is just 1 over from the carbon and the double bond. Yes. There we go. Cool. Okay. So, wow. This is the first kind of family. These are going to be the kind of ways that we do tricky mechanism things with it. Let's go on to the second family of reactions, the redox reactions. So, who remembers from general chemistry doing something called like oxidation number? And you would like have this formula that you would have to find the oxidation number of like a metal or something. So that's far too complicated. We don't need to do math in here. I don't support that. I don't endorse it. And chemists are lazy. And so what we have for organic chemistry is this concept called oxidation level. So oxidation level is kind of a shortcut of the Gen Chem thing, where it tells us how, quote, oxidized a carbon is. And we say the oxidation level of a carbon is given by how many bonds it has to an electronegative element. So for example, this carbon has 1 bond to an electronegative element, to this OH, so it's oxidation level 1. This one has 2 bonds to an electronegative element, so it's oxidation level 2. This one has 4 bonds, oxidation level 4, and so on. So what does it mean for a carbon to be oxidized? What's the whole like oil rig? Oxidation is what? Anyone? Losing what? Electrons. Oxidation is loss of electrons. So what do we mean that this is more oxidized, that this carbon has lost more electrons? Because if we look at it, they both have octets, right? Like this has an octet, this has an octet. So why are they different? Well, it's because these are polar bonds, right? This oxygen's more electronegative, so you have partial minus, partial positive. And as you accrue more of these bonds, you're going to get more partial minus going away and get more of these kind of dipole moments where you have more of a positive charge at the carbon. So it's kind of like these are bonds where the electrons are not being shared equally and they're being shared further away from the carbon. So we say the carbon is kind of losing the electrons that they would have had if they were sharing it in like an equal bond. So in that way, these are more oxidized than these. But why do we care about all of this? The general reason that we care about the oxidation level is because things that have the same oxidation level react in similar ways. So one that you've seen is all the reactions that we did in lecture 3 and the amine-enamine, they were all for ketones and aldehydes. The reason why it was for both of those is because they were both at oxidation level 2. They react very similarly. Then in lecture 5 yesterday, you learned some of the oxidation level 3 compounds, and they all react in similar ways because they're all at the same oxidation level. So the oxidation level gives us kind of a proxy of how it's going to react. The level 1s you're going to learn in lectures 6, 7, and kind of 8. So we're kind of moving our way through all of them. Now, oftentimes we like having families of reactions that kind of work within the same level, but also it's helpful to be able to move between these oxidation levels. So let's say you want to go from a level 1 to a level 2 state, you would need to oxidize. Or if you want to go from level 3 to level 1, you would need to reduce. And we have some friends that can help us with that. So meet the players. Our oxidizing agent here is chromium tetroxide, or not tetroxide, trioxide, sorry. And our reducing agent is an old friend, lithium aluminum hydride. Now, this might be a little bit weird, but these reactions are going to do some heavy lifting for us in this course. And so could we take a moment to show appreciation for them and just give them a round of applause? Thank you. God bless. So these are going to become close friends. You're going to use them probably every synthesis question going forward. And so you want these to be on hand, as these are the guys to call, who you're going to call redox reagents. I don't know. So chromium usually has a little sidekick, pyridine, which you can just abbreviate PYR, and it acts as a base. But the fun thing about these is these are redox line reactions. So we have not taught you the mechanism. You are not responsible for the mechanism for these. All that you need to know is what thing you add and what you get out. So that to me is a little bit easier. It makes these a little bit less tedious than all the full mechanism ones. So let's say you want to go from a primary alcohol to an aldehyde. What oxidation level is a primary alcohol? 1, because we have one bond to an electronegative thing. What oxidation level is an aldehyde? 2. So we are doing an oxidation. So we're going to call our oxidizing agent chromium trioxide, CrO3. And then we're just going to do it with pyridine. It's a little partner, Batman and Robin, saving the day, oxidizing. Then for the next one, secondary alcohols, they're going to form ketones. We go from oxidation level 1 to 2. So that's normal. But woza. And the third one, we start with an alcohol and we go to a carboxylic acid. What's its oxidation level? 3. So we are going +2 for the oxidation level. So pyridine is nice and all, but we need to call in some reinforcements. Specifically, we need something that is going to add this extra oxygen on to the carboxylic acid. And so the source of this extra oxygen is water. So if you want to go all the way from a primary alcohol all the way to a carboxylic acid, you need to have chromium and you need to have water. And so these are where the oxygens kind of end up here. Now, reducing, if you have a carboxylic acid and you add a lot of lithium aluminum hydride, what you get out of it is a primary alcohol, which that's very similar to what we did of double addition to esters with lithium aluminum hydride. We got a primary alcohol out of it. But interestingly, we could do this with an amide. And then what we get is not an alcohol. We don't do a double addition and get an alcohol. We get a double addition and we get an amine. So at some point in the mechanism, you don't need to know why or how, we kicked off H2O instead of our amine here. What oxidation level did we start at with an amide? 3. And then what oxidation level did we end up at with an amine? 1. Because that carbon has one bond to an electronegative atom, nitrogen. And the same thing for the one above it. Carboxylic acid was 3 to alcohol 1. And then this explains kind of why we group nitrile in with the rest, because what's nitrile's oxidation level? 3. So even though all of her sisters have a carbonyl and she doesn't, she's not bitter. She's still part of the family. We love her just the same. At least we tell her that. Here, this is kind of weird. We not only add hydrogens to the carbon when we attack a nitrile with our reducing agent, we also add hydrogens to the nitrogen over here. So what you end up doing is adding 4 hydrogens, and this will specifically make a primary amine, whereas this one you could have a secondary amine or a tertiary amine. Now, one thing I want to flag for you that I don't think Tim really mentioned is these 2 reactions to make amines are the only reactions in the entire course that we are going to teach you that make amines. So if you see a synthesis or a box problem where your final product is an amine, you know that you have done one of these reductions. Cool? Yeah. So if you had this amide and you erase it, now it's a secondary amine. But if you had this amide and you erase it, now it's a tertiary. Or if you had NH2, now it's a primary. Cool. Okay. So all of these, the reducing agent, we're using our strong reducer lithium aluminum hydride, so we go down 2 oxidation levels each time. So this really, you just practice it with line reactions. So let's look at some of the line reactions and the homework. Huh? Okay, great. I know. No, I'm so close to getting it. How do I just? Can someone help me out? What do I do to make it a split screen? Hmm? And then like, ding dong, thank you. And then I just bring up the other one. Cool. Great. So we're going to keep the line reactions over here for you to see. And then what we are going to do is we are going to go and look at these practice problems. So several of these are from challenge problem 3, and then the others are from page 6. And for right now, I think that would be helpful to just do these 3. So with each of these, do you want me to just do them with you, or do you want to try to attempt it on your own first? Try on your own, and you said do group. Other opinions? Yes, let's do that. So what I'm saying is an ester in the starting materials, and what functional group in the product? Carboxylic acid. Ester. Then the next thing I'm thinking is what are reactions that are connected to these? So esters, then the first thing I think is double addition. But double addition, we can either double add like carbons or double add hydrogens. Do we have the same number of carbons in the starting material in the product? Like here in the starting materials, we have 1, 2, 3, 4 carbons. How many do we have in the product? 4. So we didn't double add carbons. So maybe we did a double addition of hydrogens. Okay. Now carboxylic acids. Well, one way that we haven't gotten to yet is, or that you talked about in last lecture, but we haven't talked about in section yet, is taking an ester to a carboxylic acid. But what are other functional groups that we could turn into a carboxylic acid? Alcohols. And there's one more that we could turn into a carboxylic acid. It's one that we did not write explicitly, and so I think it's a little confusing. Well, the intermediate here is we first make an aldehyde, and then that aldehyde goes all the way to a carboxylic acid. So we could have an aldehyde and turn it into a carboxylic acid too. So I brainstormed the reactions that are connected to this. Because I only really see one way forward from the ester, I'm just going to try doing double addition. So what reagent double adds hydrogens to this ester? Yeah, that's like an exam 1 question. So when we do that, at our carbonyl spot, we're going to plop on 2 hydrogens there, and then we'll have an OH after the acid workup. And then we still have these other carbons and an OH on the other side. Interesting. So here we have 2 alcohols, and we are trying to make carboxylic acids. So what reagent could we use to go from an alcohol all the way to a carboxylic acid? Thank you, chromium. Yes. So we take our CrO3 H2O, and that's going to take both of these alcohols to carboxylic acids, and we will be at our product. Okay, maybe let's think about the next one together. What functional group do we have in the product? Acetal. One of the first things I think to do when I see an acetal, which you probably learned as you were practicing for the first exam, is to try to disconnect it and see what carbonyl came before this. So what alcohol and carbonyl came and made this acetal. Take a few seconds, try to write out what you think the carbonyl and the alcohol were that came together to make this acetal. Just doing your thinking backwards arrows. How'd you do with your thinking backwards? So we want to get these two pieces together. Once we have these two pieces together, we could add acid and we could make this. Okay. Well, so does this look more like piece A or piece B? Piece A, our starting material looks like piece A. How can we turn our starting material into piece A? What reagent would do that? Say again. So you're so close. So sodium borhydride would take A to this. But we want to start here and take it to a carbonyl. So are we oxidizing or reducing? Oxidizing. We have one bond to an oxygen, two bonds, so we're oxidizing. What's our oxidizing agent? CrO3. Yes, of course. See, this is why I said we should clap for them. We should know their names. They're celebrities. They are gods among us. And then do we use pyridine or water? Pyridine, because we don't need to add another O. So now we've made this piece. So all we need to do is add the other piece, an acid, and we're done. So the reagent that you should write here, this diol, H+, and we don't need a third step. Last one together. So what functional group's in the product? In the product. In the product. Yeah, we have an alkene and an amine, so it's an enamine. We only know one reaction that makes enamines. So let's look back at our notes. So we're looking at the hydrolysis. We want to be able to start with our enamine and just draw what the ketone and the amine were. So let's come up with a fake mechanism to do that, where we can just draw what the carbonyl version should be. So the thing that I'm thinking to do is cut the single bond to the nitrogen and pop an H on, and then that's how we get our amine. And then on the other one, make everything a single bond and then add a carbonate. Did that generate our products? Like, have I written the products from the enamine version? Have I lost everyone? Pause. People in my section have heard me talk about fake mechanisms. People not in my section, do you know what I'm doing and why? Or are you kind of like, what's up? Like, a fake mechanism is just a tool for us to use to draw what the product is going to be without having to think through the whole mechanism. Because this question, line reactions, do not care that you know the mechanism. They only care that you can write the product or that you can think backwards. So by having a tool of like, okay, we cut this bond, grab an H, that's what makes this guy. And we make the single bonds pop on a carbonyl, that's what makes this guy. That is a tool that's going to help us. So can you try to do that disconnection over here and see what carbonyl and what amine came together and made that enamine? So do your little disconnection and try to draw what the ketone aldehyde and amine were that came together and made this. And then we'll check and we see if we got the same thing. How'd you do? So here we cut, we put an H on, so that's our amine. Over here, we made everything a single bond, and then where we cut, we put on a double bond O. There was a little H that was here all along that we've just written out explicitly because it's an aldehyde. Now, this is one that you might not have been able to do that quickly, or you might not have been able to do it correctly yet, but you know it's a skill that you need to practice. Does this feel okay, what we just did? Okay, work. Okay. So based on that, if we look at our starting material, it's pretty clear if we call these things A and B, our starting material made A, right? And then B is something that we had to supply later. So how do we turn our starting material into A? Are we doing an oxidation or reduction? Oxidation. What's the oxidation level of this? 1. What's the oxidation level of this? We're going up, so we did an oxidation. Great. So what is our oxidizing agent? Chromium trioxide. Are we going to do this with water or purity? Why? Because we stop at the aldehyde. If we want to go all the way to carboxylic acid, we use water. So, okay, that takes us to A. And then to make our enamine, we need to include this. So we need to put in our nitrogen. And I think we say like pH around 5. I'm not sure if that's going to be in all the answer keys. You might just put the nitrogen on it, and then the reaction conditions are assumed. But that's it, another two-stepper. Questions on these box problems? Here. pH around 5. Like we're doing this in an aqueous solution with a pH of around 5. Yeah. Again, we might not write this every time. I think that if you just wrote this, that would be fine. Okay. So that's that little family, and you can see that they are going to be very helpful. They're going to be coming up a lot. Let's talk about the other family. Ugh, that's a lot. Carboxylic acid derivatives. So we're essentially talking about things that look like carboxylic acids. So they are going to have an oxidation level of 3, and we have several different flavors. One of the useful ways to think about these different molecules and different functional groups is about their reactivity, like how reactive something is. And that's going to be really helpful for us when we're trying to interconvert between them. So your most reactive is an acid chloride because it has a really poor resonance structure. All of these have resonance structures, but this one's a poor one because chlorine is huge, carbon is small. So she's very reactive. Acid anhydride has resonance structures, but the lone pairs in this auction are very confused and troubled because they could go to the left and do resonance over here, or they could go to the right and do resonance over here. And while that might seem great, it might seem like, wow, we have options. It's actually more like neither of them gets as much resonance as they would have gotten if there was not a choice. So this situation is called split resonance, and split resonance is destabilizing. And so it's not going to be as good as just a single resonance. Then esters and carboxylic acids are pretty similar in terms of reactivity. They both have a resonance structure where there's a positive charge on oxygen, which isn't great, but it is what it is. But then compared to an amide, which has a resonance structure with a positive charge on nitrogen, which one's better, a positive charge on oxygen or nitrogen? On nitrogen, because we would want a positive charge on the thing that's less electronegative. So here, amides, because they have this more stable resonance structure, they're less reactive. Beneath that, we have a nitrile. And nitriles are kind of weird because if you attack them, you're attacking a pi star CN. And if you have a pi star CN versus a pi star CO, which is higher in energy? The CN is higher in energy. And it's because the O is more electronegative, so it would be lower in energy. And generally, we want a lower energy LUMO. We want to have as small a gap as possible between the lowest unfilled one and the highest filled one. Now, at the very bottom, we have a carboxylate, and its resonance structures are completely equal. And so she is so stable that she does not want to react. Like, if you tried to have a nucleophile come in and attack here, that just wouldn't really happen because she has all this electron density around her. She's not going to be a good acceptor. So we have these different levels of reactivity of these molecules. All of these molecules have some potential leaving group, something that could be kicked off. So they have similar kind of mechanisms. And then for like acidity and basicity, like the most basic atom in all of these is the carbonyl oxygen. And then the most basic acidic proton is typically on the functional group, or it could be one of those alpha ones, the ones that are next to the carbonyl. But what does all this mean? Why do we care about it? So this whole family of reactions, the CAD reactions, our only purpose is to interconvert between all these different functional groups. So we're trying to convert between them. And the big idea here is everything can go down in reactivity really easily. Like we could go from an acid chloride to an ester down in reactivity in a single move. We could go from acid chloride to amide in a single move, ester to amide in a single move. But if we were trying to go from amide to acid chloride, there is no one reaction that does that. We're going to have to go through two reactions, a little bit more complicated. So we can always move down in reactivity, and that's going to be easier to do. And the other kind of big idea here is everything can interconvert with a carboxylic acid. So your strategy is if you have an amide and you want to make an acid chloride, well, first turn your amide into a carboxylic acid, and then turn your carboxylic acid into an acid chloride. So this chart, I think, is going to be helpful for y'all. Right now, this is the draft version. I had something come up yesterday, so my section notes aren't as complete as they normally are, and they aren't as nice. I'm going to make it look prettier. But this chart kind of takes all the line reactions from lecture yesterday for the carboxylic acid derivatives and says, okay, which directions can we go if we're trying to interconvert here? This way we cannot go, so the only route that we can do is going carboxylic acid up. The other thing I want to say about these is we spend a lot of time writing out all the mechanisms for these, and they are mechanisms that you need to know, but also like they're not that interesting for most of them. Like most of them are doing steps that are very similar to like the acetal mechanism that you've already learned. And the main way that we're going to test you on this family of reactions is as line reactions. We care that you know about converting between these functional groups at the line reaction level. And so just don't be too worried, I would say, about the mechanism. Still go through and study it, but you need to get a functional use of this. So let's try to do some problems that are connected with this, some like box problems. So I think some of these are on challenge problem 3 and 4. I think I'm going to do the challenge problem 3 and 4 ones first, just because those are the ones you haven't seen. So let's start off with this one. What functional group do we start with? We have an ester. What functional group do we end up with? Acid chloride. Are we going up in reactivity or down in reactivity? Up. So we're not going to be able to do this in a single step. So our strategy is we need to slide over from ester to carboxylic acid and then slide up to acid chloride. So for ester to carboxylic acid, we look at our chart table, we could do it in acid or base. Acid is fewer steps, so I'm just going to do acid. H3O plus. And you could also write H2O, but H3O plus gives all the information you need. And then we're at a carboxylic acid. And then what we add to go to acid chloride is just Socyl 2. Done. It's not deeper than that. Like, yes, if you were trying to think through the mechanisms, this would be a lot. But again, we care a lot more about you being able to interconvert between these functional groups as line reactions. So these are going to be far more like knowing the chart, knowing the direction, and then also like knowing the reagent. So flashcards will probably help for these. Okay, what functional group do we start off here on the next one? Acid chloride, good. And then what functional group do we end up with? Who, who is she? An enamine, you're very close. So if it was an enamine, you would have the double bond here right next to the nitrogen. But because it's 1 over, it's not an enamine. So what is it? Not an amide, because amide would have carbonyl. You maybe said something, but it was very quiet. Amine, it's just an amine. Is that also what you just said? Work. I'm really bad with the whispers. So, do you remember what I said about amines earlier? Yeah. So let's look at that reaction. So we either made it from an amide or we made it from a nitrile. Now, what type of amine is this? Primary, secondary, or tertiary? Tertiary. Well, nitriles only make primary amines. So what was this right before it was an amine? It was an amide. So the amide version would look like this. Okay. So now we have to ask, how do we make that amide from this acid chloride? Well, that's just converting between the CADs, right? So let's look at our little reaction tree diagram thing. Okay, well, we're trying to go from acid chloride to amide. What we do is we add our amine in excess, or we add our amine with pyridine. Groovy. Work. Let's do that. So, ooh, what amine should we add though? How do we determine what our amine is? Yeah. Mhm. See, this is a really easy fake mechanism. You break the bond, put a chlorine on one side, hydrogen on the other. Great. So let's add that amine. And we'll do it in excess. That's going to take us to this bad boy. And then how do we go from our amide here down to the amine? Are we changing oxidation level? What oxidation level do we start at? What oxidation level do we finish at? So if we go 3 to 1, is that an oxidation or a reduction? It's a reduction. Yeah. So what's our reducing agent? That's the one. We are almost done. I see all the like gears stopping turning. The lights are on, but no one is home. And then we're done. Yeah. To show that I'm intentionally not using it. Like in the key, you'll just see an X there. It's just really for me a thing to say, oh, I didn't just not finish this question. I'm actually saying actively, I don't need that. You don't have to, but like, no, yeah, not at all. Okay. Probably the last question we'll do, and then I guess we're skipping peptides, which is sad because I wanted to talk through a synthesis with y'all. But let's look at this last one here, which is on challenge problem 4, I believe. So we start off with a carboxylic acid and this DCC girl and an amine. Well, DCC is going to be in the next section to talk about. But essentially, what DCC does is DCC is the matchmaker, and we'll go and grab a carboxylic acid, grab an amine, and say, get married. And so that's what she does. She brings together an amine and a carboxylic acid and makes an amide. And she shows up in our CAD reactions as a way for us to go from a carboxylic acid to an amide. They're both at the same oxidation level. So we just have to figure out what amine we want to add, and then we put it on. So over here, DCC is joined together this carboxylic acid and this amine. So can you try drawing what amide she makes? Try drawing what the product of just this first reaction is going to be, where we take our carboxylic acid and we add on that amine. And I just wrote out the ethyls like this. But that's all we have. Okay, now if we have an amide and we add lithium aluminum hydride, what functional group do we make? You look disgusted. Did we have another situation recently where we had an amide and we added lithium aluminum hydride? In which case, what functional group did we make? An amine. So amide, lithium hydride, we should make an amine. What amine should we make? How should we change this? Yeah. It is that easy. If we go and look back at this, our fake mechanism, like here we put on H's, but those could just be implied, right? Like CH bonds. So it's literally like erase. And that's how we get to the product. So our product here looks like this. She has a special name. Her name is triethylamine. She has a cool cousin. So the cousin, instead of 3 ethyls, it's 4. So it's tetraethyl. And it looks like a man doing a dance. So he's tetraethyl ammonia man. So this is the kind of like skill of like putting it together. And also this is the type of thing of like, you just learned these reactions on Thursday, yesterday, have not had a chance to see it. And we're already trying to like piece together multiple reactions from different families. And that's kind of where we're going. And so like, this should feel uncomfortable. This should not feel super secure. We should probably also be feeling like, well, I don't know that I could do all these arrows, the curved arrows, because we haven't talked about that. That's something that you'll still need to review. But I'm sad that we did not get a chance to talk about peptides. I have the lecture notes on it. The big like highlights are just, you need to know how to make an amino acid from an aldehyde. And that's called the Strecker amino acid synthesis, where these reagents, you just have to memorize them. But they are just piecing together some reactions that you've seen before of we make an amine and then we hydrolyze a nitrile and we turn a nitrile into a carboxylic acid. DCC we talked about for a second, but DCC could lead to chaos because it will take any carboxylic acid and any amine and try to make a pairing. So you could get the one that you want. Like if we're trying to make that bond, we could get that. But you could have 2 of the same molecule like react with each other, and then we get just the R1 here, the yellows on it. You have 2 of the other one just react with itself. Or you could get 1 of each, but they're not connected on the right side. Like you want this orange one to be where the carbonyl is. And instead you have the orange one where the nitrogen is in the peptide bond. And so we use protection groups. We use BOC2O to protect amines. We use esters to protect carboxylic acids. And I have 2 BOC2O amines that I like of therapist. Bok chicken doesn't exist and can't hurt you. And then you have Bok running around crazy. And then instead of this, you should do TFA, which takes it off. But, and then the other one is this creepy Phineas and Ferb one of like, I'm protecting my child, the free amine, from unwanted side reactions. Work, that's a weird note to end section on, but thank you for coming today. You've had a long day. Please rest tonight. The problem set and the active are due Monday, which I know is short. So just rest tonight. Give yourself a little bit of break. Yes, I'll be sticking around to answer some questions and I hope you have a good weekend. Yeah, thanks. Zoom folks, I'm sorry I didn't do peptides. Not this weekend because I have to grade. Yes. You too. Yeah, give me 1 second to just end this now.